Testing, 1, 2, 3. Looks like it's working. Okay, we are about to begin in just a second. Hopefully people can join. All right, looks like people have begun to join, which is great. So let's go ahead and get started. Welcome to the 11th live lecture for the POSA Communications MOOC. This is the final lecture. What we're going to be doing today is going through a couple of patterns that are left over. We have the proxy pattern and we have the broker pattern, and we'll throw a little bit of adapter pattern in just briefly because you have to understand the adapter to have the whole view of things for the broker. But those are the patterns we're going to round out the course with. As you undoubtedly know, the course is kind of officially over this Wednesday when the remaining peer assessments are done and submitted. And then I think we take a couple days off, and the next course begins pretty soon. I think it might start a week from Wednesday. I'll have to go and double check that, but I seem to think it starts on the 17th of June. The next course, as you probably know, is the cloud computing course. And in the cloud computing course, we'll be talking about a variety of topics related to structured data access, both from the client side, the Android side, as well as, of course, from the cloud side. That's the main focus of the next class, is going to be the cloud side of things. But we'll also talk about how to connect Android client devices to cloud services and how to cache information and exchange information between the client device and the web service and vice versa. So that'll be coming up next. We'll be putting the videos online fairly soon. If you want to get a head start, you can take a look at the bulk of the videos. They're on Jules White's YouTube page. I provided a link to that the other day. I'll probably send that link out as an announcement here shortly. And so I encourage people who want to kind of get an early head start on the course to start watching some of those videos, because they'll figure prominently in what we'll be covering in the MOOC itself next time. But that's next MOOC, so let's try to see if we can finish off this MOOC. And in order to do that, we will start by talking about the proxy pattern. So let me go ahead and bring up the proxy pattern. Here are the slides for the proxy pattern. And whoops, that was a mistake. There we go. All right, I think that should be visible. So we're going to start off by talking about the proxy pattern in general. We'll talk about some of the issues that motivate it. We'll talk about its intent and other capabilities. And then we'll turn around and we will talk about how it's used in Android in a couple of different ways. As you probably know, the proxy pattern is something that comes from the couple of different places, actually. It comes from the Gang of Four book, and it also comes from book number 1 in the POSA Communications MOOC, or sorry, the POSA 1 book on a system of patterns. And you can find out more about the proxy pattern if you don't have these other books, which I highly recommend you get them. If you don't have these other books, then you can always take a look at this link to get more of an overview of the proxy pattern. So let's start by kind of giving a motivation for the pattern. What are some of the things that require its use, or challenges you face that can be resolved or alleviated by applying this pattern? So it's often infeasible or even impossible to access objects directly. In particular, if you're programming an Android and you have objects that reside in a server process that's different from the client process, then because of the very nature of processes in Linux and Android's use of Linux and so on, you can't just directly make a method call on an object that lives in another address space. Now, the good news is that Android provides the binder framework, which gives you a high-performance inter-process communication mechanism. So because of that, then all of a sudden it becomes possible to access these things. And we'll talk more about that in a second. Another motivation for the pattern, or maybe more of a context issue, is that you often want to be able to rearrange the way that your objects are deployed in your system as your requirements or environments evolve. So you might start out with a program where everything is co-located in the same address space, and then as you get some more experience with it, you might decide you want to move some of the processing to another process. And we've talked about the reasons for doing this before. Some motivations are you want to be able to share the objects with other applications. You don't want them to just live within one application, so that would be one motivation. You might also want to protect the client applications from things that might go wrong in the server application. So if the server hangs or crashes, you don't want the client to be disturbed. And then you may also, this is more of a Java-centric thing, you might want to isolate the clients from the garbage collection related overheads of the processing that takes place in the server process, because server process and client process are garbage collected in a different way if they're separated. They don't all get garbage collected at the same time. Okay, so the problem here, of course, is if you try to make your objects talk to each other in a manual way, you have a lot of marshalling and demarshalling of messages, and you have to figure out the message format. You have to pass those things back and forth using messengers, and that's just tedious, error-prone, and potentially inefficient, because you'll have to do things that could be optimized away if you had a higher level view of the whole thing. It's also, of course, time-consuming to have to rewrite and reconfigure and redeploy the components or objects across an application's address spaces as the requirements and environments change. So you really like to make that as easy as possible to evolve without a lot of extra work required. So the solution, at least a piece of the solution, not the entire solution, but a piece of the solution, is to define a proxy that provides a surrogate through which clients can access remote objects. So the clients don't actually access the objects directly, they access the objects through a proxy. Now, there's a bunch of different ways to implement this. Here's one way to do this in the context of Android. A service can implement a binder object that a client can't access directly, since it could be in a different process. So we've been looking at these examples, say, for the weather service application that we did, where we have different kinds of weather call objects or weather request objects that are inheriting from binder ultimately, and they are defined inside a context of a service. And then you can have a proxy that represents the interface to this binder object in such a way that you can access it correctly without having to worry about the low-level drudgery of marshalling and demarshalling its various parameters that are being passed to the method call. The client then invokes a method on the proxy which has the same name as the actual object, and then it depends, of course, on whether this is going to be running in the process or out of the process, and that depends on the Android manifest file. We'll talk a bit more about that later because there's some subtleties that are involved here that you need to understand. And the proxy pattern then works to forward the request over to the server side, where it's turned into a method call on the remote object, where remote, of course, means in another process on the same device in the context of Android. Now, the actual communication that takes place from the proxy to the server object uses something called the broker pattern, and we'll talk about that later. All right, but let's talk about proxy first. So the intent of this pattern is to provide a surrogate or placeholder that allows one object to control access to another object. And as I mentioned before, this is a gang of 4 pattern as well as a POSA pattern. They both appear in the books. You can find more about the pattern here. You should apply this pattern if you need a way to get a more sophisticated reference to an object than is possible with just a simple pointer or a simple reference. So in other words, you want to be able to have a way to access objects that may not live in the same address space that you live in. And so a pointer or a simple pointer or a simple reference can't do that for you. So you need a more sophisticated reference, and that sophisticated reference will actually point to a proxy or be a proxy. You also want to do this when you want remote objects to look and act much like local objects or local components from the client's perspective. This is easier said than done, but you want to make it easier to do this, not necessarily seamless, but more seamless. And you also typically use proxies when you have a need for statically typed method invocations, when you want there to be type checking that's done on the caller's side that's able to ensure that the data that's sent over to the server is formatted properly so there's no surprises when requests show up at the server. So here's the way that you actually organize this particular pattern from a structural point of view. You have something called the subject, which has an interface, and that would be, in this case, that would be done with an AIDL interface in the case of Android. So you define an AIDL interface that defines the subject. You would then have a proxy, which implements the same methods or method that the subject interface implements. In the case of Android, that would be the generated stub.proxy class, which we'll look at shortly. And then finally, there's something that actually does the real work, and that's the real subject. That's the guy that's going to actually implement the methods that are invoked on it. And that, of course, would be the generated stub and the implemented interface that implements that stub by subclassing and overriding the various methods that are defined in the interface. And of course, the way this works under the hood is that you have an invocation from a client on a proxy, and the proxy turns around and invokes the request method on the real subject. Now, this is a very simplified version of the proxy pattern. The one that we'll see used with the broker has a few extra steps, but this is the basic building blocks of the pattern. Here's another view. This is more of a dynamic view. In this view, the client invokes a method on the proxy to make a request. The proxy performs some pre-processing, marshaling the message, putting it into a format that it can use to send across address space boundaries. It then invokes the method and passes it over to the real subject, which unpacks it and does its thing. And then the real subject sends back the result, and that's post-processed or unmarshaled, and then the call returns to the client. That, of course, is assuming we're doing a two-way call. As you know by now in Android, you can also do a pair of one-way calls to do something similar to this, although it's not a blocking mechanism. But in both cases, proxies are being used for both one-way calls. So those are basically the steps that are involved in using the proxy dynamically. There's some good things that come from using this pattern. It helps to decouple the client from where the actual object implementation resides. It simplifies the programming of very tedious and error-prone details. Here's some of the generated code you would see if you looked at the proxy implementation. We'll look at this code in more detail. Who the heck wants to write this code manually? Well, obviously the answer is nobody, because it's really, really tricky and it's boring, and you don't want to have to do this code. It's very, very error-prone. So you'd rather have a tool that does it for you automatically. There are some downsides, of course. There could be some additional overhead if the proxy implementation is not done efficiently. Good optimizing compilers for generating the proxies can do a pretty good job, actually, of optimizing things that most programmers probably wouldn't think to do of themselves, because that's just the virtue of using compilation as a mechanism. And the other problem, of course, with proxies is there may be an overly restrictive type system that forces your application into the Procrustean bed of a certain set of methods. And if your implementation changes, you may have a lot of proxies that have to be redone. and that can be tedious also to do. And there's all kinds of workarounds for that. We won't go through them in detail here, but there's other patterns like extension interface or reflection that you can use to make that problem go away. Another consequence that's a potential drawback is you can't entirely shield clients from problems with inter-process communication across processes or networks. So just because you have a proxy doesn't mean that everything is going to magically become reliable. There's still a lot of other things that can go wrong with the communication path, and it's really the job of other parts of the middleware, like the broker, as well as the job of the application to be prepared to handle exceptional conditions that arise in ways that probably wouldn't occur if you were entirely co-located. So you have to be prepared, for example, to catch things like remote exceptions and so on. There are many, many known uses of proxy. Obviously, from the early days going back about 30 years now, we have remote procedure call middleware like Sun or ONC RPC, or the distributed computing environment, DCE, Corba, and Java remote method invocation, Java RMI, and DCOM are all examples of kind of proxy-based approaches that were popular back in the day. They're less used now, but they still are used. Local middleware on smartphones like the Android binder, that of course implements the proxy pattern. And the binder mechanism on Android actually is an enhancement of an earlier mechanism called the open binder that appeared with the BIOS system, where some of the Android developers got their early start. Okay, so that's basically a quick overview of the proxy pattern from a simple perspective. Let's now go ahead and talk about other aspects of this pattern, and we'll look more from an implementation point of view. So let me go ahead and share my screen. Okay. We're now going to talk about the implementation aspects of proxy, and we're going to talk about how it's applied in the context of Android. So one of the decisions you have to make when you use the proxy is, do you write it by hand, the old-fashioned way, or do you auto-generate it via some kind of tooling? And I think it's fair to say that the general trend these days is to do things in an automated way. Another implementation consideration is whether you should be caching information that is unchanging about the subject, so you don't have to access it remotely every time. Some information changes every time, some information doesn't change, and so you could actually cache it locally. So that's another implementation decision. In a language like C++, there's some really clever things you can do with operator overloading, with the overloaded arrow operator, or the so-called delegation operator. And so you can kind of write proxies that are nicely abstracted away from the application, and you can actually put some cool logic in operator arrow. I won't talk about this code in detail, but if you're curious about it, take a look at this paper about thread-specific storage, and it'll talk about how this gets implemented. Let's talk about how the proxy pattern is applied in Android. So when you write an AIDL file, for every AIDL file, there's actually another file that gets generated in the gen directory by the AIDL compiler. And inside that file is basically the code that is used on both the client side and on the server side. The server side code is the stub code, and the client side code is the proxy code. So here's just a little snippet of the stub code. We'll look at this later. So here's the stub code that you would go ahead and implement, or subclass, in your server side implementation, typically inside a service. And then there's a method that the stub constructor calls attach interface, and that basically attaches the implementation to the interface. So these things are now connected from the server side's perspective. Then there's also some code that's generated that's part of the stub, and this code is actually called by the client application in the on-service connected method, which is either something you would write, or if you use my generic service connection class, it would do this for you automatically. And this is called the as interface method. And as interface basically takes a binder object, which is essentially the raw channel that came from a service, and it turns it into a proxy. So down here you can see that this object is converted into a proxy object by as interface. And this gets called on the client side. Here's what the proxy class looks like. This is actually nested inside of the stub class for some crazy reason. And so they have proxy, which implements the interface. In this case, we had an interface called iDownload, but you could call it whatever you wanted to, of course. And this has the proxy constructor, and the proxy constructor takes the basically the reference to the server side object implementation, the remote object implementation, and it stashes it away in a local data field. And so this is called on the client side, and it stashes away a binder, which is used ultimately to access the server object. And then the method here, this is the download image method, which is what would be called to download the image. This goes ahead and takes a string as the URI, and this is the code that's automatically generated by the AIDL compiler. This code is called on the client side, of course, when you invoke the download image method on the proxy. And you don't really think of it as the proxy, but that's what it is. It's a proxy under the hood. So what happens here, this code is automatically generated based on the type information that was in the AIDL interface. And it goes ahead and it obtains a parcel to store the data that's going to go over to the object in the service. And it also creates a parcel to hold the reply data that comes back. And then it goes ahead and it writes the URI string into the data as a string. And then it calls the transact method. And the transact method, as you can see, is going to be invoked. And that's going to actually deliver the data and the reply message over to the remote object. So this is going to actually go across the process boundary, across the binder driver to the remote binder object running on the other side. And we'll see what happens in a second when that gets on the server side. When things come back, we check to see if an exception occurred, and if so, there's an exception that's thrown. If there's no exception that occurred, we take the reply and we read a string out of it, and we store that back in a Java string, and that gets returned as the return value by the proxy. So this is all the code that's automatically generated for you, and it's called on the client side. Now, let's take a look at the server side. The server side actually implements another pattern called the adapter pattern. And the pattern is used to convert the interface of a class into another interface the clients expect. So in this case, it's converting between the low-level format that's used to pass these parcels around across address space boundaries. And then it's turning that into a call that's the download method on the download interface, or the iDownload interface. And that's what's expected by the client and, of course, the service. And it allows classes to work together that otherwise couldn't because of incompatible interfaces. So it's basically allowing things to work together seamlessly. And you can read more about the adapter pattern here. So the adapter pattern is just the server-side dual or complement to the proxy pattern. And here's what it looks like. There's a method called onTransact that's called back by the binder framework. So the binder remote procedure call framework triggers a callback to onTransact. This is the adapter. This adapter takes a look and says, aha, this is the download image transaction. Let's go ahead and read the data out of this thing, which is in a string format. And then let's go ahead and call the download image method, which of course is an abstract method from the point of view of this stub class, but you would override this stub class and fill in download image. And let's pass it the string parameter that we got out of the parcel that came in. And then let's take the result and we'll put it into a string. And then we'll go ahead and write that string back into the reply parcel, and then that gets returned. So this is the code that's called back on the server side. So onTransact gets called back, and it basically demarshals the data by converting the parcel format into native Java format, and then it calls download image, and that's the method that we actually implemented. And so that gets called back. So this is sort of the adapter pattern. It's the complement to the proxy pattern. So to summarize this pattern, Android generates proxies that implement the proxy pattern. They allow you to do this remote method call or remote method invocation style of inter-process communication. There's no syntactic difference between a call to a co-located versus a remote component. They both have the same call syntax. However, the semantics between co-located and remote calls are subtly different, and I'll talk more about that in just a second. Okay, so this is a good time to take any questions, if anybody has any questions. While I'm waiting for questions to come along, I'm going to bring up something I want to show you based on the discussions we had last time during the virtual office hours. Let's see if there's any questions, and then I'll go ahead and cover this stuff. By the way, you can also ask questions if you want about the programming assignment review as well. So what I'd like to do here is I'd like to come back and show you a few enhancements I made to the implementation of my solution for assignment number 3. And some of this stuff was driven by the differences in semantics between co-located and remote calls. So just to recap the issue here, if you take a look, here is weather request AIDL, and you can see that weather request AIDL has a method called get current weather. That's a one-way method. It takes a location, and it also takes a results callback object. Okay, so that's what it's going to take. Now, the tricky part about this is over here in the client side code, when we do a get current weather call, if it's the two-way call, this call, of course, has to run in a background thread on the client side. So we need to be able to do that because we don't want to be doing blocking two-way calls in the main thread of control, in the UI thread. So that call is in a background thread. We're in good shape. Down here, and we're in good shape here because whether or not the weather service sync implementation is configured to run in its own process or not, the semantics from the client side will be the same. Everything will be fine because we're always running in our own thread of control, or in a background thread of control. So for example, if we have the weather service sync implemented in the same address space, that's fine because we're doing this in a background thread. And if weather service sync is implemented in a different address space, we're also fine because when it runs in a different address space, then the two-way calls run in a pool of threads, or a thread from a pool of threads managed by the binder framework. And for every two-way invocation, a different thread from the pool is going to be used. And if we're co-located, then we run in the same thread as the caller, but that's okay because we're running in a background thread anyway. So everything's fine from a two-way call perspective. Things are more tricky, though, from a one-way call perspective. Here's the one-way call invocation. Now, the way things work with one-way calls, if we are running with a co-located weather service async implementation, and we're co-located, then the one-way call will run in the calling thread, which in this case is the UI thread, because we didn't spawn a separate thread to do this. So the problem we have is if we're co-located, now this call is running in the UI thread, and that would be a problem, of course. So we're going to see how to fix that. Of course, if we're not co-located, then this invocation will run in the UI thread, which is fine, and then it passes the data over to the service, and if the service is running in its own address space, it will be running in a background thread out of the pool of threads that are managed by the binder framework. But there seems to be a tricky situation with one-way invocations. Unlike two-way invocations, if a one-way invocation is running in another process, all the one-way calls from a given client appear to run in the same background thread as opposed to different background threads. So keep that in mind when we're about to talk about the next thing here. All right, so that's the client side. Here's the service side. So that the weather service sync, it doesn't matter whether it's co-located or remote. The logic is exactly the same because we handle that on the client side. Weather service async, however, is more subtly different. And you really got to think carefully about this. So here's what I did, and I'll talk this through, and then I'll talk about the variants of this. So what I do is my get current weather implementation creates a runnable, and the runnable is where we actually go and invoke the call to get the weather service code using the JSON, using a method that'll return JSON. So get weather results will do this. And that, of course, that call is a blocking call. And when we're done, we'll either send the results back if we succeed, or we'll send an error message back if we fail. So here's where things get kind of clever. So keep in mind, we're on the service side. And the service is either in its own process or it's in the same process where the UI thread is. And we can check this by calling looper get main get thread and checking to see if that's the same thread that this method is being called on. If it is, then we're in the UI thread. And if we're on the UI thread, then we're going to go ahead and run the runnable in a background thread that we allocate out of a thread pool. And I'll talk more in a second about why I did it that way. So if we're co-located, then we run our one-way call in a background thread to avoid problems where you can't block the UI thread and make a networking call on it. Otherwise, you'll get an exception. Down here, if we're in this particular implementation, if we're not on the UI thread, that indicates we're running in a background process. And then we just simply go ahead and call the run method on the runnable directly. And that's fine because we're running in the background process. Now, for this particular application, this design is fine. We've made it so it works correctly whether or not we're co-located or remote. And since this client only lets one thing happen at a time, there's no sense fretting about trying to make this service run each of those requests concurrently. However, if we had a service who had a client that could invoke multiple requests concurrently, and we wanted those things to run at the same time, then we would come over here, and irrespective of whether we were on the UI thread or not, we would simply go ahead and execute this thing in a background thread. And that way, even though we were doing one-way calls, each one-way call would run in a separate thread out of a thread pool managed by the executor service. And the particular thread pool semantics I use here are basically going to be the cached thread pool, which will dynamically create a new thread every time a request is made. There's also a fixed size thread pool that bounds the number of threads. So anyway, I wanted to kind of show you this more sophisticated way of handling the differences in semantics between co-located and remoted invocations in AIDL, especially for one-way calls. This is very, very subtle code, and it's not surprising that a lot of people get it wrong and they have bad surprises because it's done in a very ad hoc way by the Android developers, primarily just to make the infrastructure easier for them to implement. Okay, so let's go ahead and take some questions. Are we going to have a Java concurrency MOOC? Yeah, that would be great. We're not having a Java concurrency MOOC anytime soon. We might do that at some point in a while, where a while is probably a year from now or so. So for the time being, if you want to learn about Java concurrency, which is a vastly more comprehensive topic than Android concurrency, the best place to go is either my CS282 course, which covers basically Java concurrency, and you can see videos available on the website on my YouTube channel for CS282 from the 2014 semester, talks a lot about Java. Or if you're a Safari Book Club member, I highly recommend you take a look at my Java concurrency live lessons course, which has very slickly produced professional quality videos with all kinds of cool animations and stuff. talking at length about lots and lots of stuff in Java 7 and Java 8. Next question, are we going to be using AIDL in the Cloud MOOC? So the answer is no. For the Cloud MOOC, we're going to be doing things a little differently. For the Cloud MOOC, we're going to be replacing the use of Android services and the use of the JSON reader and/or JSON object way of being able to download JSON formatted information from web services, and we're going to replace all that with use of retrofit, which, as you probably know if you've watched the videos for this MOOC towards the end, retrofit basically encapsulates all the low-level nitty-gritty details of marshalling and demarshalling JSON, and so you can simply make method calls with JSON, or sorry, with retrofit. So for the Cloud MOOC, we're going to not need the services, although in real life you could use services, but we're just not going to use them because we don't want to make too many assumptions about what people have to know in order to take this next class. I'm assuming most people will have taken this course, but we aren't going to enforce that by any means. So we're going to use retrofit as instead of using the services and doing the parsing and the services, and we're going to be using content providers on the Android phone along with SQLite database objects or tables in order to be able to re-implement various things. So we're going to do a couple of assignments, a couple of fun assignments in the next MOOC. The first one is going to be basically the weather service assignment redone using retrofit and content providers and SQLite instead of using services. And you'll see there's pros and cons, but it's showing you more stuff about structured data access. And then we'll also do an implementation where you write a video server as a web service, and then you'll connect to the video service using content providers and retrofit and sync adapters and all kinds of other good stuff. So we'll be introducing lots of other newer, cooler things that are very useful. Is it possible or advisable to attempt to get dedicated use of one core on a multi-core device? So you cannot easily do that via the Android interfaces. If you drop down into the native interfaces, the JNI, then you can do that. But it's probably not really a good idea unless you absolutely know what you're doing, because it's not taking very good advantage of the built-in scheduling mechanisms that are there. But it is possible to do it. It just requires programming at a different level. Questions about the videos by Jules White. There are no links. Obviously, he doesn't use PowerPoint slides. He writes everything out by hand on his very super cool light board. And so what you see is what you get. There are no additional slides or anything else other than the material that he presents there. That's one nice thing about using PowerPoint, is it's easier to have a leave behind that you can look at without having to listen to the video, but that's one of the consequences of using a light board-based approach. Relatively few updates to the UI thread have been considered, but if real-time updates to the UI thread is required, what additional considerations should be taken into account? Well, obviously, it depends on what you mean by real-time and how real-time is real-time. You can obviously do things with setting thread priorities with Java threads, and that's probably the closest thing to real-time you're going to get. There is some support for real-time like processing with Linux, although it's not going to give you the same kind of responsiveness as you would get with, say, VxWorks or more traditional real-time and embedded operating systems, RTOSs as they're called. So, you probably would get interactive real-time, which means the average person probably wouldn't be able to tell that something was not showing up on a very predictable basis. But I probably wouldn't use my Android device to control a nuclear reactor or a pacemaker or something else that really needs true real-time behavior. And as I said before, I think probably answering your earlier question, you can bind threads using Linux thread scheduling mechanisms using the native interfaces and the NDK and so on. And potentially you could even expose those up through JNI. But But be aware that Android is really not intended to be a real-time system, obviously. Let's see. So yet another question about real-time processing of camera stuff. So the best place to find out information about that is simply to go and look at the source code for the media framework that's available in Android, and they have all that stuff is available. You can go ahead and take a look at it. Sometimes some of that code is actually probably most of the time, that level code is implemented in the hardware abstraction layer by the vendor, and that's typically done in C or C++ with maybe a thin Java binding around it. But that kind of processing is typically done in lower level code using either JNI or NDK. And so they would use the lower level mechanisms. That is well outside the scope of this course. And so if you want more information about it, you probably have to go and find some tutorials about programming at the NDK level. I've seen some really good slide sets out there from various folks, and I think even a couple of videos talking about multimedia programming in Android. And that would be where I would start, with take a look at some of the videos that are out there. They probably also offer training courses and stuff, but again, that's well outside the scope of this class. Okay, lots of good questions. Let us go on now, and we will talk about the next pattern. Let me go ahead and set this up and share my screen. All right, slides are up, and the screen is shared. Okay, what we're going to talk about now is the broker pattern. This is the last of the patterns we're going to cover in this course, and you'll see how the broker pattern is a very nice complement to the proxy pattern. The broker pattern appeared originally in the POSA 1 book, and then there's been a couple of revisions of it over time as people got a little smarter about what the pattern is about and how to explain it. And you can take a look at this paper to find out more information. So let's talk a bit about why you would use a broker, what the challenges are. This discussion, again, is not unlike what we just talked about with the proxy pattern. So we've got a system with multiple potentially remote objects. They might be remote, they might be co-located, and we want these things to interact synchronously or asynchronously. And of course, the binder gives you a nice way of handling that through its high-performance IPC mechanism. And as we saw before, we don't want the application developers to wrestle with low-level message passing. We'd like to abstract those things out using AIDL. But there's more than just the AIDL part. There's more than just the interface part and being able to handle marshalling and demarshalling. There's also a lot of other issues. There's computing diversity. There's different languages, different operating systems, different protocols, different hardware. Now, Android kind of locks this down. There's obviously one operating system, and there's kind of one protocol, the binder protocol, and there's one set of hardware. But there are other languages, right? So there's C++, there's C, there's Java. Conceivably, you could have other bindings if you were so inclined, and so on and so forth. And then there's a third thing that we'd like application developers not to have to wrestle with, and those are the inherent complexities of communication. So partial failures, security, latency, all that kind of good stuff. So there's other things you got to worry about when you start sending messages or making method calls that go across address spaces. I wrote a book forward a number of years ago for a book that talked about some of these issues that you might want to take a look at. So the solution here is to separate out all the infrastructure considerations from the application functionality by providing a broker that isolates all the communication related concerns into the infrastructure. And of course, there's lots of different ways to do this. One way to do it in Android is to have the binder, and the binder is what you use to implement your remote objects. And those are ones that can't be accessed directly. And then you get a proxy from the client side, and then the proxy gets a hold of a way to talk to the binder object by the little broker mechanism that's implemented using the interaction protocol, using the service connection objects and the onBind hook method in bound services, and those basically exchange the information that's needed in order to talk back and forth. And then the client invokes a method on a proxy, and then the binder mechanism uses the stub we talked about using the adapter pattern to do what's called an upcall to the appropriate method defined on the binder object that resides in the service. And it's the broker that does all of that communication under the hood. So the broker, the proxy, the adapter, these are all used to provide both synchronous and asynchronous communication in Android. So here's the intent of the broker pattern. It basically allows clients to connect and interact with remote objects by basically mediating the interactions from the clients to the remote objects and encapsulating all the details of local and/or remote inter-process communication. You can use this when certain things apply, when applications want to do synchronous or asynchronous communication, and they don't want to have to be bothered to know whether something's local or remote. As we saw, sometimes the broker can hide that from you entirely. Sometimes you have to be aware of some of the patterns that use that stuff correctly. You also want to be able to handle faults and manage the end-to-end quality of service in the infrastructure. And you want to be able to encapsulate all the low-level systems programming details in the infrastructure. So memory management, connection management, data transfer, concurrency, synchronization. You want all those things to be hidden from the application, which just makes method calls to pass parameters back and forth. Here's basically the structure of this pattern. We have a client, which is an activity in this case, or it could be a service if it's a one-way call. We have the broker, which is really the broken up into a requester, the guy that invokes methods on the client side, and a dispatcher who receives the messages from the methods on the server side and dispatches them. And that's provided by the binder RPC framework. And then we have a demarshaller, which is the generated proxy and stub. And that's, of course, what comes out of the AIDL compiler. And then we have what's called a servant, and that's the subclass of binder that you implement the methods that get called back. So those are basically the structural parts. You can read the broker revisited pattern for more details. Here's what the dynamic part looks like. When you start up, you register the object on the server side so the client knows it exists. That would correspond to implementing something inside of a service using a subclass or an extension of the stub object. The client then gets a proxy and invokes a method, and that establishes a connection if there isn't one already. As you saw with the way that works in Android, you call bind service, and that's what sets the connection up before the method is invoked. The broker then takes the request and makes sure it gets routed to the appropriate server, where it's handed off to the dispatcher, which goes ahead and demarshals the request and dispatches it back to the method called on the object. So those are kind of the dynamic steps that are involved here. And if it's a two-way call, then there's a response sent back to the client via the broker, and that uses much the same mechanism to marshal the reply, and then the client proxy will unmarshal it and handle it back to the client. The good news about this pattern is location independence. The broker is responsible for knowing where the server and the server objects run, so clients don't need to know those details. So that's part of the brokering process and the discovery process. Obviously, Android handles all that stuff through the various means that the binder framework provides. There's a nice separation of concern. You can change the server implementation without affecting the clients as long as the interfaces don't change. Your code becomes much more modular, reusable, and portable because the broker is hiding all those details. Obviously, in the case of Android, you know you're programming on Android, but if you were using a more powerful broker framework such as Corba, then you can get language independence, operating system independence, network protocol independence, hardware independence, and so on and so forth. And under the hood, there, of course, are all kinds of interesting patterns being applied for doing all this type of thing. There's additional time and space overhead. Applications using the brokers can be slower because there's extra work going on. Although, if your broker is implemented wisely, you might actually get better performance than a typical hand-coded solution because the broker implementer might be a lot more savvy about how to do these optimizations than the average application developer would. whenever you start doing distributed systems or systems that are split across address spaces, things may fail, and you have to be prepared to handle failures at any given point in time. So your code could be less reliable. That's not so much a consequence of the broker, just a consequence of distribution. May be complicated. The debugging may be more difficult because when things go wrong, you have to either think about the client side being wrong, the server side being wrong, or heaven forbid, the broker implementation being wrong, which is really very annoying because then you've got to go and debug the broker code. But if the broker is robust, of course, that shouldn't happen a whole lot. Here's a number of known uses. I'll talk about some technology known uses, and then I'll give you some sort of human known uses examples. So the classic example of the broker, of course, is the Common Object Request Broker, CORBA. Broker is basically its middle name. And in that case, you invoke a method call on a proxy, and that converts the method to a message. The message is sent to a server, which could be started up on the fly. The server receives the message, and it has a couple layers of demultiplexing to get that message turned back into a method call on the actual object implementation. The thing about CORBA compared to Android is it's much, much more transparent with respect to the expectations of what a client and server have to do. Client and servers are gleefully unaware, client server objects at the application level are gleefully unaware that all this stuff is taking place. Whereas with Android, a lot more of this code gets thrust into the application's awareness by callbacks and other kinds of things. So the Android broker is not as sophisticated as, say, CORBA, but it fits nicely into the Android model of doing things. And given the appropriate abstractions, like the generic service framework or the generic connection framework that I showed you, you can hide a lot of those details for the most part. CORBA also is trying to solve a different problem. It's trying to make things be application independent, or rather language independent, OS independent, network independent, hardware independent, location independent, et cetera, et cetera. Android, of course, is another broker implementation that is not quite as transparent, but it's still very powerful. So broker is used in a lot of places. There's lots of open source implementations of things like CORBA. I've helped implement something called DAO, which is the ACE orb, which is widely used still in places that need the high performance of something like CORBA. And actually, if you look carefully at the broker pattern, it's actually a pattern language. And there's actually, gosh, a dozen or so patterns that go into implementing broker. We've seen a couple of them: Proxy, we've seen Adapter. There are other ones that we really didn't talk about much, but we've talked about in the class, like Activator, and so on and so forth. So there's lots of different ways of thinking about this stuff. There's also, of course, human known uses of the broker pattern. A good example of a human known use would be something like a real estate broker, where the two parties who are trying to buy or sell real estate don't have to directly talk to each other, but instead they talk through each other mediated via a broker. And so the seller says, you know, here's my asking price, and the buyer says, here's my offer, and the broker is then responsible for shielding the buyer and the seller from the details of communicating with each other. And of course, they're also responsible for taking care of all the legalistic issues about titles and mortgages and other kinds of things that you need to do in order to inspections and all this other stuff that are handled through the broker. Maybe another example that would be similar, like a general contractor. If you're building a house, you, the builder of the house, would interact with the general contractor, and that general contractor would be responsible for talking to all the subcontractors to get the work done. Okay, so that's basically the broker overview. We'll talk about the broker implementation in just a second. But first, there are some questions. An important aspect that is not part of this specialization is Android user interface design. Is there any plan for adding a course on this? Well, obviously, the first two MOOCs in the series taught by Professor Porter talk about Android user interface programming and you know, how to program with the Android user interface widgets and all those kinds of things. So there's plenty of coverage in the first two courses about how to program Android user interfaces. There's 8 to 10 weeks worth of stuff on those topics. If you're asking more about questions about, say, using Android material design patterns and how to program that, that's a good question that you should ask Professor Porter, not me. I'm not a UI person. I'm a infrastructure concurrency communications person. So that's really a better question to ask him. He has actually created a live lessons course also. So if you're a Safari Book Club member, he has a course out on Android design, which really does cover those design issues related to material design and other kinds of design issues, responsive design, and so on. So you might take a look at that if you have access to the Safari Book Club. And of course, there's lots and lots of other places to learn about Android design paradigms and patterns, but that's not something that I cover. So I will not be responsible for those types of things. When considering AIDL, 2 requirements are IPC and multi-threading. That is very good. Yes, absolutely. So in assignment 3, it's natural to use AIDL to avoid writing tedious code. Yes, I agree. Are there other patterns we can consider for assignment number 3? Well, so yes, and if you take a look at the walkthrough that I did from I guess it was last Friday, I did a code walkthrough of my solution for assignment number 3. And that solution is absolutely chock full of patterns. Some of the patterns are kind of gang of 4 patterns. So you'll, of course, find patterns in there like template method. You'll find patterns in there like factory method, of course. So those are just classic patterns we use all the time. Other patterns are more sort of Android client-server architectural patterns. So obviously, we just talked about broker and proxy. Those are in there. But we're also using other things. If you take a careful look at the way that we structure the solution, it almost always has the same look and feel. If you look at the acronym application, the weather service application, pretty much all the applications that we've been talking about in the class have a very consistent look and feel at this point. We tend to use the memento pattern along with a retained fragment manager in order to be able to do things related to making it easy to rotate your phone without losing state. So that memento pattern is a good example of a pattern that gets used a lot. A lot of the implementations use the bridge pattern. This particular one doesn't, but if you go back and look at the solution for assignment number 2, I did, that's heavily based on the bridge pattern, just because I was trying to abstract away from whether or not we used bound or started services. So those are very common patterns to use. And then we also see a bunch of other, sort of POSA patterns. We see command processor used a lot of times. We see active object used a lot of times because we're using the Android components like the intent service or the hammer framework that does those things. In cases where we use the async task mechanism, which we do in assignment number 3, of course, that's really implementing the template method pattern as well as basically the half sync, half async pattern, which is another pattern. And then of course the implementation of the async task framework is using various patterns like command processor and active object. So again, very common. But and then we use strategies all over the place. So in fact, I'll talk in a second about a strategy for doing caching. And so lots of places where we have interfaces separated from implementations. That's really the strategy pattern in the gang of 4 sense. So there's lots of patterns. There's other implementation patterns like activator that we've talked about at various points. So lots of good things you can look at from a pattern-oriented perspective. Using threads often result in leaking memory. To avoid this, you should always use the services. Is this true? No, absolutely not. There's really no good reason why using threads should leak memory. In fact, if you go back and you take a look at the material we covered in the first POSA MOOC, the POSA concurrency MOOC, I showed how to use various patterns like the memento pattern and other patterns for being able to program threads correctly, multi-threads correctly, without having to worry about leaking any memory. So if you are careful in using your patterns and your idioms for using the hammer framework and combining them with gang of four patterns and POSA patterns, there's no good reason to be leaking threads. So leaking threads is not necessarily the best reason to use services. The best reason for using services is that the amount of effort required to write your code properly that's multi-threaded is minimized from the client point of view if you do your threading in the service side. You still have to know some other things, though. You have to know how to use other mechanisms, like if you're using bound services, you have to know how to use changing configurations to avoid shutting the service down prematurely if you want it to continue running in the background when the activity is reconfigured, and so on and so forth. So the way I would recast your question, Ramil, is really to say, to write proper multi-threaded code requires knowledge of patterns and frameworks. And sometimes if your services have if your applications have certain characteristics, then having your multi-threaded code run in services is a good thing to do because it simplifies some of the programming. But that's by no means a universal statement. And there's plenty of situations where doing things in an async task, or even a thread for that matter, is perfectly fine as long as you're aware of the consequences of state management when your application is either rotated or destroyed. So you have to make sure you shut things down properly. And that, of course, requires knowledge of cancellation idioms that you use in both Java and Android. So once again, knowledge of patterns is crucially important to being able to write successful code. Let's see. Maybe we should consider writing code to detect patterns which could be more applicable to certain code. Well, so there's a couple things to think about there, right? So one thing to do is to either use auto generators like the AIDL compiler, which bakes the patterns into the generated code, right? So AIDL bakes Proxy and adapter into the code that's generated. So in that case, you're not really thinking about those patterns anymore. They just happen to come out of the generator. Another thing to do is to program using frameworks, which also encapsulate many of the roles in a pattern. What's a good example? Well, obviously the hammer framework, the async task framework, the intent service framework, the whole binder, AIDL, broker stuff, all those things bake in activator, command processor, active object, proxy, bridge, broker, adapter, all those patterns get baked in. So using either frameworks that come out of the box with Android or additional frameworks you might write on top is a great way of being able to get those patterns largely for free. There still will often be some roles in the patterns you have to fill in, usually hook methods of some form or another. But a lot of the actual heavy lifting is done underneath the scenes, behind the scenes, so you don't have to worry about it. So writing code to detect which patterns to use, that's really a research problem. There are people who've worked on this particular problem, and you can probably find some tools like refactoring tools that will take those things into account. But that's by no means something that just you can do trivially, right? It takes a lot of thought. So you're probably better off for now, as we wait for research to mature that will automatically refactor your code to identify what patterns to use. You're probably best at this point advised to learn the patterns, look at examples that are pattern-based, learn the frameworks, write frameworks, apply the patterns, and then be prepared to do lots of code reviews and refactoring. If you want to see examples of that, just go back and watch the evolution of the solutions in this particular MOOC over the past 5 weeks, and you'll see that I keep learning new things about how to better reapply and refactor the code, so it's much more extensible and easy to understand and so on, and much more pattern oriented. All right, good discussion about lateral thinking, always a good topic. There are software patterns that can be applied to human processes, just like we would do in software. Absolutely, that's the case. But you could also use patterns to help programmers work together more easily and collaborate. Absolutely. So there's a whole body of literature about patterns for teams to work together more effectively. And some of the people who are well known in that space would be people like Jim Copleen or James Copleen. He goes by both names, but he goes by Jim, but his name is James. So James Copleen has written a lot of articles about patterns for team-based development. If you Google agile patterns, you'll find stuff about how to do agile methods using patterns for agile approaches. A lot of the people who were big into the agile community, people like Kent Beck and Alistair Coburn, Robert Martin, also have been very, very influential in the patterns community. Jim Copleen, I'll add him, Ward Cunningham, all these famous names from the agile world are also patterns people, and they look for recurring solutions to problems in contexts, no matter where they are. And I'm pretty much the same way. I look for the same thing in concurrency and communication. Let me do one more thing while we're talking about patterns, and then we'll go and wrap up here. I want to show you a revision of the executor cache. Let's go find that. So this, of course, by the way, just to be patterns oriented, this is really the bridge pattern or the strategy pattern. I guess it's really the strategy pattern. We have a timeout cache interface that defines the methods that we need to implement. And then we can have different implementations of these. So this is basically a strategy called the executor service timeout cache. And this implements the timeout cache interface. It extends the ref counted interface. And here's the implementation. And I want to just go over this real quick because I added some cool new stuff to it. So it's even more robust, but no less efficient than before. So the way this works is we use a magic piece of software out of the Java util concurrent package called concurrent hash map. And we use something else out of the Java util concurrent called scheduled executor service, which basically allows us to schedule things to run at some point in the future. And we have one thread that does that. We then have a class called cache values that keeps track of the key and, sorry, it keeps track of the value, and it keeps track of a future that's associated with a key that's registered associated with that particular key. And it's going to use that, of course, to cancel this in the future. We have a constructor that takes the value and stores it, and we have another method called set future that's a setter that sets the future. You'll see why we have to split those apart in a second. Here's the put method. This is what I changed from last time. The implementation I had before had a race condition where if you registered a new item in the cache, you would have the potential to have that item immediately removed if the old version timed out before you could cancel it. So this new solution fixes that problem in an incredibly clever and efficient way. So let me show you how it works. So when put is called to add something to the cache, you're going to put the key into the cache with the value for a particular time, let's say 10 seconds. We create a new cache values object, which stores the value, and we make this final, and you'll see why we need to make this final in a second. We then come down here and we create a new runnable called cleanup cache runnable. Cleanup cache runnable has a run method, which when called will remove the key. Recall the key was defined up here as a final, so it's going to remove the key from the cache. However, it'll only remove the key from the cache if the current value associated with the key is this version of cache values. And every time we call new, of course, we're going to get a new version of this. We're going to get a new pointer, a new reference. So this will only take the key out if it matches that cache values. All right, so keep that in mind. That'll be important here in a second. We then come down to the schedule method. We schedule this cleanup cache runnable to run some number of seconds in the future, let's say 10, and we get back a future, and then we go and we set the future value in cache values to the value that's returned from schedule. And even though cache values is final, we can still change its state. We just can't change what it points to. We then come down here and we call the put method, passing in the key and the cache values, which now have both a value and a future. And put will atomically store the new values with the key and return any previous cache values that were there. And that's all done atomically. So this is the only place in this method where any locking takes place. And under the hood, it uses an extremely efficient compare and swap method done in a hardware with help from the virtual machine. And then down here, if there was indeed a previous value there, we go ahead and we cancel its future, and we tell it to cancel it immediately. And that way, if we put something in the cache that was already there, we will register it for another timeout period and cancel the original timeout period. Now, the cool thing about this is even though there's a window of time between when we put something in and when we go ahead and cancel it, because we use this magic remove method, if the method is triggered, the cache values that are stored under that key name will be different from the cache value that we had stored earlier that we're now in the process of canceling. So it'll turn out that this cancel method, this remove method, will actually just ignore canceling the values if the key doesn't match the old cache value. So if cache values is updated, it will not be removed. Anyway, that's basically the implementation change. The get method remains exactly the same. We atomically get the value, and if there was one, we return it. If there wasn't, we return null. And then remove simply removes the item, the key from the cache. And then the close method, which gets called when its reference count drops to 0, will shut down the executor service. At any rate, I just wanted to show you that particular bit of code because I thought it was kind of cool that you could make an almost imperceptible change to the implementation we had before, and all of a sudden there's no more race conditions. That's kind of neat. Okay, let us go now and we will cover the final topic in the entire MOOC, if you can believe that. And here it is. Let's go ahead and bring this up. So we're going to talk now about the implementation of the broker pattern. This broker pattern is implemented in Android, but we're going to talk about the steps that are involved in implementing it. So the way this works is you start by defining an invocation interface, and this is how you invoke operations and pass them from client to server. All the source code we're going to talk about here is in the binder.java file. This is the client part. There's also, of course, a C++ part. This is the Java part, rather. There's also a C and C++ part as well. So this is going to give us an invocation interface that allows clients to construct and send requests. Notice that this interface is kind of low level, right? We're calling transact with the operation we want. We're passing in the data that's been marshaled and the reply that we're going to get the results back in and any flags. And then under the hood, this thing is going to call, it's going to call on transact. And that'll, of course, then actually do the real work to get things sent over to the server side. And of course, we're relying on the proxy pattern to make this easier to program. Nobody would want to write code at this level. We then select and implement the marshaller. And the proxy pattern, of course, is how we do this. This is the bit of the code, just kind of showing you what the proxy looks like for our download image application. So this is all the proxy related stuff. We select the communication protocol, and there's a bunch of different choices that are described in the actual pattern description itself. There could be connectionless protocols, connection-oriented protocols, and so on. The actual protocol that's done in Android is implemented by a kernel driver, the binder driver, and it uses ioctl or IO control methods to send and receive chunks of data at the very, very low level. This is in the native sort of runtime level. So this is C and C++ code, and it's passing over these data structures from client to server and then back later. In a real implementation that was network oriented as opposed to the one we have here that's just running in Android, we'd have to figure out how to do the networking portion, and you would probably use things like acceptor connector and reactor, which are other patterns that are described in the POSA 2 book, and also you can read about them here at this link. There needs to be resource management for managing pools and groups of things, such as pools of threads or pools of buffers and so on, and we'd use caching and pooling patterns that appear in the POSA 3 book. You can also read about them here online. So as you know, in Android, we have a pool of threads, for example. We have a pool of messages that are used, and so on and so forth. We define a registration interface, which is used to essentially register and unregister the servants. These are the implementation artifacts. There's this thing called attach interface, which basically is used to connect the stub with the underlying broker or binder framework. You can see the code there, how that works. You need a mechanism to reference servants, and that, of course, is used to pass the binder object references back and forth via the onBind hook method that exists in a service. That's how that gets sent back to the client via the bind service call, which then uses the service connection handshake to get back the binder. And so onBind is basically a factory method that returns a binder object. You can see the source code here for more information about how that works. Here's how this gets passed back to the client via the onServiceConnected method. You can see that code here if you want to read the code. And then you need a mechanism to transform request messages into up calls on servants. And that's done by the stub, which implements the adapter pattern. We kind of talked about that before. And then you have to decide if you want to support asynchrony or not. And of course, Android makes that easy by using one-way calls and having the asynchronous semantics that we've talked about many times now in the course. You may also want to optimize things for local communication. So it turns out if you're talking to something that's co-located in your same address space, then you don't need a proxy. It'll just give you back the object directly. And so they actually bake this into the as interface method call. They decide whether something's local or remote, and then they'll give you back an optimized implementation in the case it's going to be a local co-located call. And you can find out more about co-location optimizations at this paper I wrote a long time ago. Android, of course, applies the broker pattern all over the place. Anytime you use basically AIDL, you'll use broker. And so one case where they do it is in the network settings activity, which is part of the activity manager service, or rather, sorry, the activity manager service is playing the role of the broker here underneath the hood. And when you call start service, it goes ahead and starts up the network query service. You can find out more about the network query service. This is used to basically find out what kind of network settings your phone has in terms of, say, GSM versus CDMA and so on and so forth. And underneath the hood, then once the service is started, you call bind service to get back the binder object. And then if you look at the source code, you can see all this works. And then you invoke methods, basically passing in the parameters that you want to call, and those things get executed in the service by using the broker pattern to deliver this stuff across the way. So that's basically how it all works. There's lots and lots of other examples. That's just a very simple one. What's kind of interesting about this is this one is also one that shows the use of asynchronous communication by passing one-way methods, just like we did for the weather service. Okay, so to summarize all this stuff, we use the broker pattern to invoke methods across processes. You could also use this to evoke methods in a same process, but especially in the case of Android, that's really overkill. You're better off doing other things and not using broker unless you're going across address spaces. You could also, of course, use the command processor pattern. So these patterns are essentially pattern complements. They can be used together. They can be used either one implement the other. They can be used for solving different problems, different places. We use command processor when we want to pass messages around, when we use, say, the intent service. We use broker when we want to make method calls and use AIDL. So those are two different ways to do things. And so if you're a software architect, obviously you have to understand these patterns and understand the trade-offs between them. Okay, so I think that is the end of that section. If there are any questions, I'd be happy to take them. Looks like we're kind of running down on time. As always, I greatly appreciate everybody who's shown up to the live lectures and virtual office hours. That really makes the class a lot more fun to teach. I've certainly learned quite a bit more, I think, by doing it this way than I would have if we just recorded all the lectures, because the questions that come up and the interactions we have always forced me to learn something new about Android I didn't quite know before. I didn't know how to articulate it in a logical and sequenced manner, so that's really great. This, I think, also has the distinction of being the very first entirely live MOOC done on the Coursera platform. I guess I should preface that or qualify that a little bit. Not everything was live. There were obviously recorded lectures, both of the material we covered and as well as other stuff on the HTTP processing that Professor White did. But as far as having weekly interactions on a regular basis live with Google Hangout, I think we're the first one to try to do that. And I think it's really an interesting format. If you have any thoughts about it, you ought to share them with the Coursera folks, because I'm sure that they would be interested in knowing what works and what doesn't. I certainly find it to be much more fun to do it this way, but you may feel differently. And since most of you have taken a lot more MOOCs than I have, you probably would have a better insight about whether you like this format better or worse than anything else that you've done. Okay, well, again, thanks everybody very much, and get your peer assessments done, and I will look forward to joining you in the next MOOC, which will start up again in the not too distant future. So thanks again.